Welcome, everyone, to the deep dive here on the YouTube channel. If you found this, you're likely looking for the shortest, most reliable path to understanding this whole longevity revolution.
That's right. Without wading through, dense scientific texts for weeks on end.
Exactly. So you are definitely in the right place. Our goal today is basically a complete deep dive.
We're aiming for a comprehensive extraction, really, going straight into the core insights from the book Super Agers, an evidence-based approach to longevity.
Think of this as getting the entire book's key knowledge, the actionable stuff, all in one place. We want to help reset your expectations for what human health span can and honestly probably should look like.
Absolutely. The landscape is changing fast.
Okay, let's unpack this and jump right in. It really does feel like we've shifted almost overnight, seems, from sort of vague health advice to genuine targeted science. What's actually fueling this massive change right now in extending health span?
It's what the author calls the Great Convergence. It's this really powerful meeting point. You've got foundational breakthroughs in life science colliding with the sheer power of information technology, IT.
So it's tech meeting biology.
In a huge way. We're seeing decades, literally decades, of patient fundamental research finally paying off. Big time. All at once.
And you're not just talking about the last few years, right? Give us a sense of that history.
Oh, absolutely not. Think about the timelines here. It's been, what, over 20 years since we first sequenced the human genome?
Right, that was huge.
Huge. Then 10 years since the discovery of CRISPR, the genome editing system. That was a watershed moment.
Definitely.
And maybe less known, 30 years of slow, steady development in the mRNA and lipid nanoparticle delivery systems.
Yeah.
The tech behind some COVID vaccines.
Ah, okay. So that groundwork was laid long before the pandemic.
Exactly. And now, layer on top of that the recent explosion in large language AI models. Suddenly we have this incredible computational power to analyze all the data these other breakthroughs are generating.
Wow. So it's like cumulative. Hundreds of years of scientific effort converging right now.
That's a great way to put it. It gives us this unique, really enviable starting position for what comes next.
And all this science, all this history, it kind of boils down to what the book calls the 5 dimensions that are transforming health span.
Precisely. These are the 5 pillars, you could say. And the really crucial thing to grasp is that they're all interconnected. They all influence each other.
Okay, what are they?
We're talking about cells, genomics, lifestyle, the microbiome, and then drugs and vaccines. And like I said, they interact dynamically. Your lifestyle choices, they directly impact your cells and your gut microbiome.
Right.
And discovering new drugs, that's being massively accelerated by AI and our deep understanding of genomics. We can't think of these as separate silos anymore. It's one big ecosystem.
Okay, let's start with cells then. That feels like the fundamental building block. We hear this number, nearly 37 trillion cells in the body, which is just mind-boggling.
It is staggering.
But the new insight isn't just the number. It's that we can actually, manipulate them now, rebuild them, thanks to sequencing tech.
That is the core revolution right there. We can now tinker with the inner workings of individual cells with unbelievable precision. Take T cells, for example. They're critical for your immune system.
Okay.
Historically, the immune system was kind of a black box, but now researchers can literally take your T cells out, engineer them in the lab in vitro, and then put them back into your body to achieve really specific, powerful results.
And what kind of results? What does that engineering actually do? How does it change treatment for big diseases?
Well, you see it working in 2 main ways. First, you can engineer these T cells to dramatically rev up the immune response against really aggressive cancers that maybe didn't respond to treatment before. That's the whole CAR-T revolution you hear.
Right, ERR.
ERR is a chimeric antigen receptor. Think of it like a high-tech GPS system bolted onto the T cell. It lets the T cell find and just obliterate cancer cells it would normally ignore.
Wow. And is at the other side?
The other side is suppression. You can engineer T cells to actually suppress a faulty immune response, like in autoimmune diseases where the body attacks itself.
So you can either boost it or calm it down with precision.
Exactly. That level of biological control, it's changing absolutely everything in medicine.
Okay, but that kind of precision must need an incredible amount of information, right? How are scientists even handling the sheer volume of data needed for this? Which I guess brings us to big data in these longitudinal studies.
Data is absolutely critical. It's the fuel for this revolution. And one of the most important resources here is the UK Biobank study. This thing is massive.
Tell us about it.
They followed over 500,000 participants 502,000 people for nearly 20 years, and they gathered everything: their complete genome sequence, electronic health records, detailed medical scans, plus all the long-term follow-up data.
20 years of data on 500,000 people.
Yeah. And this resource is generating what the book calls seminal new insights. We're finding completely new biomarkers, non-traditional risk factors, stuff we just couldn't see when we only studied smaller, isolated groups of patients.
That sounds amazing. But hang on, a huge data set doesn't automatically mean the findings apply to everyone, does it? Especially with genomics being linked to ancestry.
That is the crucial caveat, and it needs
Mhm.
to be, shouted from the rooftops. The UK Biobank, despite its size, is overwhelmingly not diverse. About 94% of the participants are of white ethnicity.
94%. Wow.
Okay.
Okay.
So that severely limits how we can generalize findings about, say, drug effectiveness or disease risk across different populations.
Yeah.
It creates real potential health equity problems down the line.
So we need diverse data.
Absolutely paramount. That's why resources like the U.S. All of Us initiative, which are focused on multi-ancestry data, are so incredibly necessary. We have to mirror global diversity if we want scientific discoveries that benefit everyone equitably.
Okay, that's a really important point. Before we get into the lifestyle stuff people can actually do, we need to quickly clarify how we should interpret the evidence. Because we're going to throw around a lot of stats. We hear about observational studies a lot with diet and exercise. What are they exactly, and why are they different from randomized trials?
Right, good question. Observational studies are basically research where scientists, observe large groups of people over long periods.
Yeah.
It's almost impossible to do a randomized trial where you force, say, half the people to eat a strict Mediterranean diet for 20 years and the other half not to.
Right. People wouldn't stick to it.
Exactly. So instead, we look at large populations and track what happens in real life.
But the data collection for those must be kind of messy, relying on people's memory and stuff.
It can be. Often it relies on things like self-reported food diaries
Hmm.
or people trying to remember how much they exercised. So while these studies provide a huge amount of valuable information, they can really only show an association,
Meaning a pattern.
a consistent pattern of benefit or harm, even after researchers adjust for known factors that might confuse things, what they call confounders. But, crucially, these studies fundamentally cannot prove a direct cause and effect relationship.
So if a study says people who eat nuts live longer, it means nut eaters tend to live longer, but maybe they also exercise more or smoke less, and that's the real reason.
That's the classic limitation, exactly. But, and this is important, when these observational studies consistently point towards an effect on what we call all-cause mortality.
Meaning death from any cause.
Right. Not just heart disease or cancer, but
Yeah.
anything. When you see that link consistently, those numbers become really meaningful. It strongly suggests there are real negative health effects happening, maybe through pathways we haven't even fully figured out yet.
Okay, so even if it's just association, a strong link to overall mortality is a big red flag or a green light.
It compels us towards certain choices, yes.
Oh.
Strong suggestive evidence.
All right, let's dive into lifestyle then. This is where you, the listener, have the most immediate power. And we have to start with nutrition, specifically the big villain, according to the book, ultra-processed foods,
Yeah.
UPFs.
Yeah, and I love the analogy the author uses here. UPS are like UFOs, alien, unnatural, industrially produced substances that are, frankly, barely even food.
And they make up a huge chunk of the modern diet, right?
Massive. And the damage they cause comes from two main angles: chemical and physical.
Okay, let's break that down. Chemical first. What are we talking about? What should people look for on labels?
It's a whole list, a real rogues gallery of industrial ingredients and additives you really want to avoid. Things like high fructose corn syrup, maltodextrin, weird fruit juice concentrates, hydrogenated oils, palm oil,
Okay.
and then various emulsifiers, things like soy lecithin, xanthan gum. The chemical damage comes from just chronically eating these compounds that our bodies aren't really designed to handle safely decade after decade.
And the physical dimension, you mentioned how they're made. High heat, pressure.
Yeah. The manufacturing uses processes like molding, pre-frying, extrusion cooking that involves really high temperatures, often over 100 Celsius, and intense physical forces.
And the goal of all that processing is?
It's actually pretty sinister when you think about it. The main goal is simply to maximize digestibility, to make it absorb super fast in your gut.
Why is that bad?
Because that rapid absorption causes these immediate sharp spikes in your blood glucose and insulin. It's the exact opposite of what natural dietary fiber does, which slows digestion and keeps your blood sugar stable.
Ah, okay, so that explains the weight gain link. I remember reading about a trial.
Absolutely. There was a very rigorous NIH trial. They put people on a UPF diet, matched the calories to an unprocessed diet group, and the UPF group gained weight. The unprocessed group lost weight.
Wow.
But it's not just weight. The consequences are body-wide. UPFs are now strongly associated with fatty liver disease, most types of cancer, depression, inflammatory bowel disease, dementia. The list goes on.
And the mortality link, that number is shocking. A 62% increase.
It's monumental. That figure comes from a huge review. 45 studies, almost 115,000 people followed for 30 years. Consuming more than 4 servings of UPFs per day was linked to a 62% jump in all-cause mortality.
And 4 servings isn't that much, is it? Give us an example.
No, it's disturbingly easy to hit. Think. A bowl of sugary breakfast cereal, a packaged energy bar for a snack, a soda with lunch, and maybe a pre-made frozen dinner. That's 4 right there.
Wow. Okay, so limiting UPFs seems like maybe the single most impactful thing someone can do.
Honestly, based on the evidence presented, it really seems that way. Huge leverage point.
Okay, let's move to trickier areas. Artificial sweeteners and salt. Sweeteners first. The data seems really confusing. Some reviews say no big deal, others link them to heart risk. How do you make sense of that as a listener?
Yeah, it's a great example of where nuance is key. You're right, some big reviews haven't found compelling evidence of long-term systemic harm.
Right.
However, the large population studies, the observational ones, reflecting how people actually use these things in the real world, they have found a direct link between consuming certain sweeteners, especially aspartame, asulfame potassium, and sucralose, an increased risk of cardiovascular and cerebrovascular disease, heart attacks, and strokes.
So real-world use points to risk, even if smaller controlled trials are less clear. What about that trial linking sweeteners to the gut microbiome?
Ah, yes. That was a fascinating, small, randomized trial. It showed that saccharin and sucralose actually impaired how well healthy adults managed their blood sugar, their glycemic response.
Okay.
And crucially, it showed that all 4 sweeteners they tested, that included aspartame and even stevia, caused changes in the gut microbiome. And we know from other research that those specific kinds of microbiome changes are tied to problems with blood sugar control.
So the overall picture isn't great, even if they're maybe better than sugar.
That seems to be the conclusion, synthesizing all the data. The evidence leans unfavorable. They're likely less worrisome than large amounts of sugar, yes, but not harmless. Stevia and monk fruit seem to come out looking the least concerning currently.
Okay. Now salt, sodium. We all know the link to high blood pressure, hypertension, but the book mentions debate about how big the effect really is.
Right. The science is clear on the link, but the magnitude is debated. A big Cochrane review found sodium restriction only led to a fairly small average drop in blood pressure, like 0.4 millimeter Hg.
Tiny.
Yeah, and it varies hugely between people. Some are very salt sensitive, others aren't. But where the risk becomes really clear, really obvious, is when daily sodium intake goes above 5 grams.
And where does the average American sit?
Around 3.5 grams of sodium a day. So most people are already sort of creeping up towards that higher risk zone. 1 or 2 teaspoons of actual salt is roughly 2 grams of sodium, for reference. Moderate intake seems acceptable.
And it's not just blood pressure, right? High salt affects the brain too.
Absolutely. High salt intake can reduce blood flow to the brain. It seems to cause dysfunction in the blood vessel walls there. That carries a potential risk for cognitive impairment, maybe even dementia later on.
Is there practical advice?
It's pretty straightforward. Try not to add extra salt to your food. Read labels on processed foods meticulously. Sodium hides everywhere. And if you have high blood pressure, and this is critical, you don't have kidney disease, consider using a potassium chloride salt substitute. Gives you salty flavor without the sodium hit.
Okay, good tips. We've talked a lot about what not to eat. Let's flip it. What about the building blocks of a healthy plate? Macronutrients. We need to cover fats, fasting, and that keto diet caveat.
Right. And the big theme here, running through all the longevity science, is that the quality or the subtype of the macronutrient often matters more than just the total amount.
Okay, so for fats.
For fats, the evidence is strong. Shifting your intake away from saturated fats, mostly found in animal products, towards plant-based unsaturated fats.
Yeah.
Think mono and polyunsaturated.
Like olive oil, nuts, avocados.
Exactly. Those are the heroes. Making that shift is strongly linked to a big reduction in risk for both cardiovascular disease and type 2 diabetes.
Okay, makes sense. What about the keto diet? High fat, super popular for weight loss. What's the book's take?
Keto comes with some pretty significant caveats that need a hard look. Because it's so high in fat and very low in carbs and protein, it's associated with things like persistently high LDL cholesterol.
A bad cholesterol.
Right, which increases long-term cardiovascular risk. Also, the keto flu, that brain fog people get. And it can promote fatty liver disease. Plus, there was this really rigorous NIH trial comparing high-fat diets to plant-based, low-fat ones.
What did it find?
The high-fat group ended up eating, on average, 700 more calories per day over 2 weeks, even when they weren't trying to track calories.
Wow. Just naturally ate more.
It suggests that high-fat foods might inherently lead to overconsumption for many people.
That makes sense why strict calorie restriction is so hard long term. Is there any consensus on that or on intermittent fasting for longevity?
General conclusions are still pretty elusive. And sticking to strict, continuous calorie restriction for decades, it's incredibly hard. And it carries risks losing bone density, muscle mass, maybe even cognitive issues since the brain needs so much energy.
So maybe not realistic for most people. What about intermittent fasting?
Small trials do show some parallel metabolic benefits to calorie restriction. But again, long-term adherence and effects are less clear.
So boiling it down, what's the most practical evidence-based advice on fasting someone can actually use?
It really comes down to simple, time-restricted eating. Eat an early dinner. Make sure you finish eating at least 3, maybe 4 hours before you plan to sleep.
And then nothing until breakfast.
Exactly. Avoid any calories until breakfast the next morning. That gives your body a natural, sustained fasting window every single day without the extreme difficulty or potential risks of severe calorie cutting.
Okay, that sounds doable. Now, exercise. Moving our bodies. We know it's crucial. But what's the actual longevity dose? What numbers should motivate people?
The dose-response data is incredibly clear on this. There was one huge study, over 650,000 people. It found that briskly walking for 450 minutes a week, that's about 64 minutes a day, was associated with living 4.5 years longer.
4.5 years longer just from walking briskly?
Associated with it, yes. And overall, increased physical activity is linked to around a 31% reduction in all-cause mortality. It's not a small benefit, it's a profound life extension opportunity.
What about the 10,000 steps goal? Is that just a random number, or does the science back it up now?
It's funny, it kind of started without much solid evidence, more of a marketing thing, but the science has actually caught up and largely validated it.
Really? How?
Well, the data shows benefits kick in pretty early, around 2,500 to 2,700 steps a day, reducing mortality risk. The benefit for mortality seems to plateau around 7,500 steps. But the absolute lowest risk in one big UK biobank study was seen in people getting between 9,000 and 10,500 steps a day.
Ah, so 10,000 is right in that sweet spot.
Exactly. So that ballyhooed 10,000-step goal turns out to be a pretty good, scientifically supported target after all.
Now, the author points out a historical mistake in how we, or doctors, advise people about exercise. What did we get wrong?
The big mistake was focusing almost entirely on aerobic fitness. Get your 150 minutes of moderate activity a week, like jogging or cycling.
Right, that's what you always hear.
But what got neglected historically was strength, resistance, and balance training. Aerobic conditioning is only one half of the equation for longevity.
Why is strength so important?
As we age, losing muscle mass sarcopenia becomes a really powerful negative factor for health and survival. We absolutely have to build in simple strength activities. Squats, lunges, using light weights, resistance bands.
And that finding about isometric exercise seems huge for people short on time.
It's phenomenal, yeah. Isometric exercise where you tense a muscle without changing its length, like holding a wall squat or a plank. Doing those for just 8 minutes a day, maybe 3 times a week, can lower blood pressure just as effectively as standard aerobic exercise or even high-intensity interval training.
8 minutes, 3 times a week. That's incredibly efficient.
It really lowers the barrier. It gives everyone a non-negotiable, time-efficient way to get that crucial strength component in.
Okay, finally in this lifestyle section, let's look beyond us to our surroundings. Environmental toxins and nature. These are now seen as major factors, right?
Huge factors, quantifiable factors.
Yeah.
Air pollution, for instance, is now considered the single leading contributor to the global burden of disease.
Wow, leading contributor.
Yeah, we're talking mainly about chronic exposure to those tiny particles, PM2.5. Scientists haven't found any safe level for long-term exposure. It's linked to inflammation throughout the body, cognitive decline, even reduced response to vaccines. And get this, it's estimated to be responsible for maybe 20% of all type 2 diabetes cases globally.
20%. From air pollution, that's staggering.
It really is. And it's not just the air outside.
Right, chemicals, plastics.
Exactly. Pesticide exposure is associated with various risks, cancers, Parkinson's, type 2 diabetes again. And then there's the whole microplastic and nanoplastic issue. It's alarming how pervasive they are.
We breathe them in, eat them.
Yep. And they've been found circulating in our bloodstream, even crossing into our brains. And the worry is they incite inflammation wherever they end up, adding to our body's overall biological stress load.
Okay, so that's the environmental assault. What's the antidote the book suggests?
Nature itself. Spending time in natural environments. The evidence is mounting.
How much time?
The threshold seems to be around more than 120 minutes per week. So 2 hours a week spent in parks, woodlands, near water, whatever. It's strongly associated with better health outcomes and higher well-being.
And there's a way to measure this. Nature score.
Yeah, it's a tool that tries to quantify the quality of nature in your immediate environment. It looks at things like tree canopy cover, air quality, noise pollution levels.
And a higher score means better health.
It correlates. A high nature score is linked to lower use of mental health services for things like stress, anxiety, depression. Biologically, being in these calmer, greener spaces lowers cortisol, reduces systemic inflammation.
And this links back to health equity, too, I imagine.
Absolutely. Access to high-quality, natural environments is often much lower for people in lower socioeconomic groups. It compounds the other health risks they face. It's a real environmental justice issue.
All right, let's switch gears pretty dramatically now. Let's talk about some of the drugs that are just fundamentally changing how we manage chronic diseases. And the biggest story right now has to be the GLP-1 drugs. Ozempic, Wegovy, Mounjaro, the weight loss results are just unprecedented.
They really are a true game changer. You look at semaglutide, the active ingredient in Ozempic and Wegovy, at that higher 2.4 milligram dose used for weight loss. Trials showed an average loss of 15% of body weight. That's around 34 pounds for the average person in the trial.
15% average is huge.
Huge. And then tirzepatide, which is Mounjaro, a dual receptor drug, actually exceeded that. At higher doses, people were losing 20% or even more of their body weight. We've simply never seen that kind of efficacy outside of bariatric surgery before.
How are they doing that? Older diet drugs often had limited success or bad side effects. These seem different, like they rewire our relationship with food, what's happening in the brain.
They work through several really sophisticated mechanisms. They tap into these dual fullness circuits in the hypothalamus, which is kind of the brain's control center for hunger.
Dual circuits.
Yeah. One seems to control pre-ingestion satiation, basically feeling full even before you've eaten much. The other handles that feeling of satisfaction after a meal, post-meal satiety.
Okay, so they hit fullness from both ends.
Right. Plus, they talk to the brain axis. They slow down how quickly your stomach empties, partly via the vagus nerve. That gives you that physical feeling of fullness for longer. And they seem to dull the sort of hedonic, pleasure-seeking drive for food.
And it seems like the effects go beyond just food cravings.
It looks that way. By acting on the brain's limbic system, the reward pathways, studies are suggesting these drugs can also reduce cravings for alcohol, tobacco, maybe even things like gambling. But honestly, the biggest, most crucial hidden benefit seems to be the cardiovascular protection.
Right, talk about that, because the evidence shows it's not just about the weight loss itself, correct?
That is the absolutely critical insight here. There was a massive trial, nearly 18,000 high-risk patients who already had heart disease. Taking semaglutide led to a stunning 20% relative reduction in heart attacks, strokes, and deaths from cardiovascular causes.
20% reduction in actual events.
Yes. And here's the profound part. The cardiovascular benefits started showing up before people had even lost a substantial amount of weight.
Really? So it's doing something else?
It seems to be. And this is backed up by seeing a significant drop in a key inflammation biomarker called high-sensitivity C-reactive protein, or HSCRP. The drug appears to be acting as a potent anti-inflammatory agent, independent of just shedding pounds. It really underscores that obesity itself is fundamentally an inflammatory disease.
Okay, that's incredibly powerful, but we have to look at the downsides too. The cost is astronomical. The book mentions $13,350 a month versus a manufacturing cost of maybe $5.
The disparity is staggering, yeah.
Yeah.
And it creates huge health equity issues. We know obesity is more common in lower socioeconomic groups, and this price tag basically puts this potentially life-saving therapy completely out of reach for many who need it most. It actively widens the health gap.
And then there's the commitment issue. Is this basically a forever drug?
As things stand now, largely yes. Most people who start these drugs stop within the first year, often due to cost or side effects. And the trials clearly show that when you stop, the weight comes back, often rapidly.
So there's no exit strategy yet.
The manufacturers haven't identified or really tested one. So you're looking at a potential commitment to lifelong, very expensive medication.
Mm.
That's deeply concerning, especially when you think about the rising rates of childhood obesity.
Hmm.
Are we talking about kids committing to decades of this?
That's a heavy thought. And there are concerns about muscle loss, too.
Yes, sarcopenic obesity. Losing muscle along with fat. It highlights the absolute need to combine these drugs with regular exercise, especially strength training, to maintain healthy muscle and bone as you lose weight.
Okay. Moving from treating obesity to preventing heart disease at its root, let's
Okay.
talk about atherosclerosis.
Right, the underlying cause of most heart attacks and strokes. The word itself, atherosclerosis, literally means hardening of the porridge. From the Greek athero for gruel or porridge.
Catchy.
Isn't it? It describes that slow, insidious process, takes decades, where LDL cholesterol and other fatty particles, lipoproteins, build up inside your artery walls. They get trapped.
And that causes inflammation.
Exactly. That buildup traps the lipoproteins and triggers this chronic low-grade inflammation in the artery wall. That inflammation is what makes the plaque unstable, likely to rupture and cause a heart attack or stroke.
We've used LDL cholesterol as the main biomarker for decades. Is it still the best, or is there something more accurate now?
LDL is absolutely validated, still crucial, but many experts, including the author, argue that apoprotein B, or ApoB, is actually a superior predictor of cardiovascular risk.
ApoB, why is it better?
Because ApoB is the actual protein, the little carrier molecule that transports cholesterol in your blood, particularly LDL. You measure the number of these carrier particles directly, and here's why it matters. About 20% of people can have perfectly normal LDL cholesterol levels, but still have high ApoB levels.
Meaning they have hidden risks.
Exactly. High risk that a standard lipid panel might miss. So testing ApoB is really important, though often still not routinely done. You can then combine that ApoB level with something called a polygenic risk score.
That sounds complicated.
It's basically a score calculated from thousands of small genetic variations that tells you your inherent background genetic risk for heart disease. Putting ApoB and your polygenic risk together gives a much more powerful personalized prediction of your true risk.
Okay, so since inflammation is the real engine driving atherosclerosis, targeting inflammation directly makes sense. The CANTOS trial was big news on that front, right?
Revolutionary, really. Cantus used a drug called canakinumab, a monoclonal antibody, specifically designed to target inflammation. And it worked. It significantly reduced heart attacks and stroke.
Without lowering cholesterol.
Exactly, without touching lipid levels at all. It was definitive proof that inflammation itself is an independent causal factor that you can target therapeutically. Now, the drug was complex, expensive, and had a small risk of serious infections, but the principle was established.
And now there's a much older, cheaper drug approved for this.
Yes, colchicine. It's an ancient anti-inflammatory drug, been around forever, usually used for gout. But large trials show that taking low-dose colchicine chronically reduced cardiovascular events by about 30% in high-risk patients who'd already had heart issues.
30% is substantial.
Very. And in 2023, the FDA actually approved a specific formulation of colchicine for the explicit purpose of treating cardiovascular inflammation. It really reinforces inflammation as this key culprit we can now target directly and affordably.
Okay, let's pivot now to some of the most cutting-edge science in the book. We mentioned CRISPR earlier, genome editing. Why is this considered maybe the most consequential life science breakthrough of our time?
It's considered so consequential because it offers the potential, for the first time really, to manage common, complex diseases by fixing the underlying genetic cause. We're already seeing it applied in cancer and heart disease, often starting with rare single-gene disorders as a proof of concept.
So this could fundamentally change medicine.
It's not an exaggeration to say that for many listeners, their children or grandchildren might well undergo some form of therapeutic genome editing in their lifetime. It's coming.
Explain CRISPR 1.0 again, the first version. Why was it called a knockout strategy?
Right, so the early nucleases, and especially CRISPR-Cas9, made it much easier to disrupt a gene. What these tools do is make a precise cut through both strands of the DNA at a target location.
Okay.
The cell then tries to repair that break, but its natural repair mechanisms are kind of error-prone. They often introduce small, random mistakes, little insertions or deletions of DNA letters. And because the CRISPR tool keeps cutting, if the target site is still intact, this process repeats until the gene is effectively scrambled and non-functional, silenced.
So you knock out the faulty gene's function.
Exactly. It's a gene knockout. The big limitation, though, is you don't really control the outcome precisely. You could break the gene, but you can't easily fix it, like correcting a single typo in the DNA sequence.
Got it. And quickly, what's the difference between gene therapy and gene editing? People use those terms interchangeably sometimes.
Good clarification. Gene therapy is typically gene addition. You often use a modified harmless virus to deliver a new working copy of a gene into cells. It works alongside the faulty copy.
Okay.
Gene editing, on the other hand, aims to make a change at the original gene's location in the genome, either disrupting it, like with CRISPR 1.0, or with newer tools, actually fixing the mistake, correcting the sequence. That precise fixing capability, using things like base editing and prime editing, is where the real revolution lies for treating genetic diseases.
Okay. Now let's apply that kind of precision thinking to cancer. The book emphasizes that fully understanding the tumor's molecular makeup is crucial now. Why?
It's become the absolute molecular imperative in modern cancer care. Getting a full molecular profile of a tumor is vital because so many of our best, newest treatments are targeted therapies. They only work if the cancer has a specific driver mutation.
Like HER2 in breast cancer or BRCA mutations.
Exactly. HR2, BRCA12, Courier AS, ALK, EGFR. There's a growing list. If you don't test for these mutations, you might completely miss the chance to use a targeted drug that could be incredibly effective, even curative, for that specific patient.
And the book highlights some tragic history here about delays in approving these targeted drugs.
Yeah, the historical delays were truly heartbreaking, cost countless lives. The author points out examples. Patients with certain lung cancers waiting years for drugs targeting specific mutations, even after they showed success elsewhere. Or delays of 6-7 years for PRP inhibitors like olaparib to be approved for cancers beyond ovarian, despite having the same BRCA mutations.
Just because the old system classified cancers by organ, not mutation.
Largely, yes. Hundreds of thousands of people likely died waiting for treatments tailored to their tumor's specific molecular fingerprint because the approval system was slow to adapt. Thankfully, that's changing.
And now we have personalized living drugs, too, ramping up the immune system.
Yes, this is the real personalized revolution. CAR T cell therapy is the prime example, taking a patient's own T cells, engineering them in the lab to hunt down their specific cancer, and then reinfusing them. It's a living drug.
Wow.
That, along with things like personalized cancer vaccines based on the unique mutations in your tumor neoantigen vaccines. These are what the book calls the quintessential individualized medical interventions. We're seeing dramatic responses even in cancers that were considered terminal just a few years ago.
Okay, that power to engineer immunity brings us nicely to vaccines. The COVID pandemic obviously accelerated things massively.
It was a global catalyst for vaccine science, no question. Just contrast the typical historical timeline, 8 to 10 years on average to develop a new vaccine. Mumps was the previous speed record holder at 4 years.
4 years is fast.
It's considered incredibly fast. Some vaccines took over 100 years. Then COVID comes along. Realistic projections were maybe a vaccine by 2033. Instead, we got multiple highly effective vaccines in months. And that incredible success really propelled the mRNA and lipid nanoparticle platform to the forefront. It's now the leading technology being explored for vaccines against many other infectious diseases and even for cancer therapies.
The success story of the RSV vaccine also highlights this new era, right? Took 67 years.
67 years from identifying the virus to finally getting highly effective vaccines. Just approved recently for older adults, showing like 94% efficacy. That's a massive public health win.
And how did they finally crack it after so long?
It was through rational, structure-based design. Scientists figured out the exact 3D shape of a key viral protein, the fusion protein, in its pre-fusion state before it infects a cell. They learned how to stabilize it in that specific shape using clever molecular engineering. That stabilized protein makes a much better vaccine target.
Kind of like how they stabilized the spike protein for the COVID vaccine.
Exactly the same principle. We're now designing vaccines based on understanding the precise molecular structures involved, not just through older trial and error methods.
Okay, and finally, the HPV vaccine. The book calls it almost superhuman immunity. Potential cancer eradication.
It's truly one of science's miracles. The HPV vaccine, given usually as 2 or 3 shots, achieves what's called sterilizing immunity. Meaning it stops the virus from even entering your cells in the first place. It prevents the initial infection entirely.
Wow.
And since virtually all cervical cancers and many head and neck cancers are caused by chronic HPV infection, this vaccine effectively eliminates the risk. It offers the genuine possibility of eradicating these common cancers completely.
But vaccination rates are low.
Alarmingly low. In the U.S., maybe only around 60% of adolescents get it. Worldwide, it's like 1 in 5 eligible people. It's a profound, tragic squandering of an incredible scientific gift that could prevent hundreds of thousands of cancer deaths every year.
All right, let's dedicate this last section to the biology of aging itself. How do scientists actually define aging now? What is it, biologically?
Generally, it's understood as the gradual accumulation of damage to our cells, our molecules, over our lifespan. This damage eventually leads to a decline in function. Scientists try to categorize this using the hallmarks of aging.
Right, I've heard of those. They recently updated them.
They did. The list expanded from 9 to 12 hallmarks, reflecting our deeper understanding of the interconnected processes involved.
Okay, maybe focus on the big ones. What are the most critical hallmarks driving age-related decline and disease?
Well, 3 core ones are often highlighted. First, genomic instability. Our DNA just gets damaged faster than our repair systems can keep up over time. Second, telomere attrition. Those protective caps at the ends of our chromosomes get shorter with each cell division, eventually signaling cells to stop dividing or die.
Okay.
And maybe the most talked about one, cellular senescence. The rise of zombie cells. These are damaged cells that basically stop dividing but refuse to die off properly. Instead, they hang around secreting a cocktail of harmful inflammatory substances that damage nearby healthy tissues.
Zombie cells. Got it. What about the newer hallmarks? What do they tell us?
The newer additions tend to reflect more systemic issues, problems with communication and the broader environment within the body. They include things like chronic inflammation, sometimes called inflammaging, and dysbiosis, meaning an unhealthy imbalance in our gut microbiome.
And how do those link to specific diseases of aging?
Critically, that chronic, low-grade inflammation and messed up communication between aged immune cells, they're implicated in driving conditions like atrial fibrillation, that common irregular heartbeat, and also sarcopenia, the severe loss of muscle mass and function as we age.
Okay. We established earlier that lifestyle is incredibly powerful. Can our choices really overcome our genetic predisposition, or are we just stuck with the genes we inherit?
We are definitely not stuck. This is perhaps the most empowering message in the whole book, that big UK biobank analysis. It showed that genetics only accounted for about 20% of the variation in lifespan.
Only 20%.
Only about 20%. But adopting a favorable lifestyle, good diet, exercise, not smoking, etc., had a huge independent effect. It actually managed to mitigate a significant chunk of the genetic risk. People with high genetic risk for a shorter lifespan who also had a healthy lifestyle lived about 5 years longer on average than those with high genetic risk and an unhealthy lifestyle.
So lifestyle can override a good portion of bad genetic luck.
It absolutely provides a powerful buffer. You have significant agency over your health destiny.
And out of all those lifestyle factors, diet, sleep, stress, not smoking, is there one that stands out as being able to actually reset our biological age?
Unequivocally, yes.
Yeah.
Exercise. Based on what we can measure with epigenetic clocks, these tests look at chemical tags on your DNA that change with age. Exercise is currently the only intervention that's been well validated in humans to actually turn back the clock, biologically speaking.
How does exercise do that?
The compounds released during and after exercise, sometimes called exerkines, seem to play a key role. They help dial down inflammation, promote cellular cleanup processes like autophagy, and generally help maintain youthful cellular function. It's like an anti-aging medicine you produce yourself.
Okay, let's talk about actual anti-aging drugs being developed. What about senolytics? The drugs targeting those zombie cells. Where are we with those?
Right. Senolytics aim to selectively find and kill off those harmful senescent cells, hopefully cleaning up the toxic environment they create. The first generation of these drugs, often combinations like dasatinib plus quercetin, are currently in clinical trials.
For what conditions?
For serious age-related diseases where senescence is thought to play a big role, like idiopathic pulmonary fibrosis, chronic kidney disease, even Alzheimer's. Early, small trials have shown they can clear senescent cells in humans, which is proof of concept.
But are they improving the diseases?
That's where the results have been more mixed so far. Some hints of benefit, but not a clear home run yet. It's definitely an area of intense research and huge promise, but still very much science in progress, not something ready for prime-time anti-aging use.
Got it. And the other big-name drug candidate often mentioned is rapamycin. How does that work and why the excitement?
Rapamycin and its derivatives called rapalogs are exciting because they target a really central signaling pathway in our cells. They inhibit a gene called MTOR, mammalian target of rapamycin.
And what does MTOR do?
MTOR acts like a master switch, influencing tons of key cellular processes, growth, protein production, metabolism. Critically inhibiting MTR ramps up autophagy, the cell's waste removal and recycling system.
So it helps clean up cellular junk.
Exactly. And inhibiting MTR basically mimics some of the beneficial effects of calorie restriction, which is the most robust way known to extend lifespan in many animal models. So the idea is that by modulating MTOR, rapamycin might favorably impact multiple hallmarks of aging all at once. Again, still mostly in research phases for aging itself, though used clinically for other things.
Okay, so promising science, but needs more time. We have to contrast that with some of the stuff being marketed now, right? The book warns about unproven, expensive interventions.
Yes, that skepticism is essential. You have to separate the rigorous ongoing science from the, frankly, scams or unproven hype. The classic example the book mentions is clinics that were selling infusions of plasma from young donors.
Young blood transfusions for anti-aging. Seriously.
Seriously, charging thousands of dollars, like $8,000 a liter. The FDA had to issue a strong warning against this practice, stating clearly there was absolutely no proof of benefit for aging or any related condition, and highlighting the significant risks involved: fluid overload, allergic reactions, infections.
So the takeaway is, if it sounds too good to be true and lacks solid, large-scale human trial data.
Be extremely skeptical. Stick to the evidence-based interventions.
Okay, so wrapping up this entire deep dive, synthesizing everything from the book, where does this leave us right now? What's the immediate, actionable path forward for the listener?
I think the core message, the real belief driving the research described, is that we are entering a truly golden time for the prevention of age-related diseases. That's the actionable part for today.
Prevention, not necessarily reversal of aging itself yet.
Exactly. Think about most major age-related diseases: Alzheimer's, heart disease, many cancers. They don't just appear overnight. They typically have a long, slow burn, a warm-up period of maybe 1, even 2 decades before clear symptoms emerge.
A window of opportunity.
A huge window of opportunity. And now we have an unprecedented arsenal to leverage that window.
The prediction arsenal you mentioned earlier.
Precisely. We can identify people at high risk much earlier and more accurately than ever before by combining all these tools. Advanced biomarkers like ApoB, polygenic risk scores looking at patterns of proteins in the blood, specialized imaging, and layering multimodal AI on top of all that data.
AI can spot patterns we miss.
It seems uniquely capable of reliably predicting tipping points, those moments when a system is about to shift into a disease state before they actually happen. And the human body, it's the ultimate complex, interconnected system. AI is poised to revolutionize prediction and prevention. Hashtag outro. So, to quickly summarize this incredibly rich deep dive into super agers, we're really at this inflection point, this powerful convergence of science giving us new control over biology. For you, the listener, the power right now lies in those targeted lifestyle choices, especially aggressively avoiding ultra-processed foods and committing to both aerobic and strength training. That's huge.
Right. And alongside that, we're seeing these breakthroughs in drugs like the GLP-1s, inflammation fighters like colchicine that are already changing the game for managing existing chronic conditions tied to aging.
Exactly. So while that sort of sci-fi body-wide aging reversal might still be down the road, the immediate massive impact comes from deploying this new knowledge for aggressive, evidence-based prevention and keeping our specific organs healthy for longer.
That makes sense. Use the tools we have now for prevention.
Which leads us to maybe a final provocative thought for you to chew on, building on the book's themes. We talked about how GLP-1 drugs help the heart before major weight loss, likely via inflammation. We talked about colchicine reducing heart attacks by targeting inflammation. It shows how treating one aspect of aging, like inflammation, can have broader benefits.
So the lines are blurring.
The lines between treating a single disease and promoting overall health span are definitely blurring. So the question to ponder is, what current treatment may be prescribed today for just one specific condition might we discover tomorrow is actually the next major key to unlocking broader longevity?
Something fascinating to think about as the science keeps racing forward. Thank you so much for joining us for this deep dive. We hope